Today is January 24th. We are going to begin our lecture on Chapter 2 today. However, before we get started, one of your classmates has asked a question, and we want to look at problem 1-50, which is a manometry problem. So, to take a look at the problem in the textbook, the water in the tank is pressurized by air, and the pressure is measured by this multi-fluid manometer, where this stem would be water, of course, because the water is being pushed up by the pressure. Then we have a height of a column of oil, and we have a height of a column of mercury, and at point 2, we are open to the atmosphere. So we're going to use 3 ideas. One of the ideas is that at every interface, the pressure will be equal on each side of the interface. So, for example, the pressure in the air is going to be exactly equal to the pressure in the water at the top. Then as we go down, we increase pressure, and as we go up, we decrease pressure by an amount of rho GH. And once again, here at 2, we're open to the atmosphere. Now, if we're looking for gauge pressure, we're going to consider the pressure at 2 to be equal to 0, aren't we? Does that make sense? All right. So we can go ahead and we can set this up. Now, in your textbook, I want to take a look at an example of a manometry problem, perhaps. There we go. Okay, so this is example 110 or 19. This is the one that we talked about earlier. Okay, so in 19 we have a single fluid manometer. But basically, we take a look at this, and if we're looking for some P, this would be the P in the gas, that's going to equal P atmosphere plus rho GH, because the pressure here is the same. Right? So basically what we're saying is there's 2 ways you can look at this. We could also say P, which is right here, minus rho GH is equal to P in the atmosphere. See what I'm saying? It's just if this term moves over to the other side of the equation, the rho GH, it's mathematically identical. So if we took P in the gas, and from that point we said, okay, we're going to go up, so that's going to be a negative minus rho GH, and then the pressure at the interface is the same, which is equal to P atmosphere, then we would just write this equation as P minus rho GH equals P in the atmosphere. And whichever way that looks more clearer to you is fine, all right? But since we're looking for a pressure in a water tank, let's look at it this way when we do this problem. All right, so similarly here, what we can say then is we know that the pressure of the air and the pressure of the water is going to be the same. So we can say P1, and then what happens? Well, our water comes to here, right? So the pressure here is equal. So in other words, we can say the pressure in the air is equal to the pressure of the water at this point. And that's what we're looking for. Make sense? Carter, does it? Sure. Oh, I'm sorry, you're right. Yes, here we go. All right, so if you look at this tank, we know that the pressure right here at this interface is going to be equal. The air pressure and the water pressure at that point are going to be equal to each other. Right? Okay. So if we start from that point, let's see if I can get this all on one page. So what we can say then is that P1, and then we are going to go down some amount and up some amount. So actually, the difference in height between the water and this, well, I don't know exactly how I'm trying to describe this. It's actually easier if I start over here. Since this is water, as we go down this amount, the water pressure here is higher than the water pressure here, isn't it? Does that make sense? Okay, so then if I say plus rho of the water, G, times this H, which is H1 plus H2. Okay, That gets us to here. Then to here we go up, minus rho water GH2. And from here to here, what happens? When we're here, we're in the mercury. And we want to come back to this point. So in other words, here we're lower. Oh, I'm sorry, it's oil, not mercury. I apologize for that. So the mercury, the oil, then we go from here to here, we go down, which is plus rho of the oil times GH2. And that gets us to this point. And then if we come around here, we have to go up, which is minus rho of the oil GH3. That is the pressure at 2, which is the pressure of the atmosphere. All right, now I've been a little bit redundant here, but I just wanted to follow that manometer around very clearly and go from one point to the other. All right, now if this were a gas and not a liquid, we really could say the pressure here and the pressure here are about the same, because the pressure becomes very distributed in a light gas. But with water, water's quite heavy, so we have to take into account the weight of that column. Okay, so anyway, so the pressure of the atmosphere, if we're looking for gauge, is 0, right? And so we're looking for this. It says taking the densities, water, oh, this is mercury. I didn't see the change right there. Where does it change? Is it right there? Yeah. Sorry, what's that? Yeah, mine's not copied very well. Yeah. Oh, thank you. I won't write in your book, though. So let's go ahead and just do this, and I'll put this right here. So it's nearly identical. It's just that we have a different column. All right. So once again, we're going to start here at P1, just like that, and that's what we're looking for, P1, and then we go down. How much? H1 plus H2. So down is plus rho of the water, because it's fluid in that column. From here to here is water, times G, times H1 plus H2, because that is the height difference between this interface and the bottom. So this plus this is the pressure right here.
Is G gravity?
G is gravity.
Oh.
Right. Then we come back up to this point. That's really it's not strange. It's fine. I guess you're going to subtract off H2 the way I have it written out. So we have, then we're going up. So it's minus rho water GH2. And then we come up. If we go from here to here, then we are coming up to H1, which brings us back to our original location, and then down to here. So if we look at the difference in the column of the oil, we're going down by H2. So then that's going to be plus rho of the oil times G times H2. And that gets us to the pressure right here. Then we come up in the mercury, which is minus rho mercury times G times H3 equals the pressure, not rho, but the pressure at point 2, which is the pressure of the atmosphere, which, because we're talking about gauge pressure, we will just call equal to 0. And at that point, you can just pull everything else over to the other side of the equation and solve for P1. And that will give you the gauge pressure of that water above the column of air. Yeah?
Question.
Sure.
So what you did with like the water when you were working with the column of water?
Yes.
You did the density of water times gravity times H1 plus H2
Yes.
minus the density of water times gravity times H2.
Yes. So it's really just times H1. If you look at
Yeah.
the difference, it's just H1. Absolutely.
Yeah, that's what I was going to ask. But
Right.
you just-
Oh, yeah. So you can just say, okay, well, look, the water starts here, and it goes to here.
Okay.
So it's plus H1.
Because then you're basically treating it the same way that you treated the oil
Yep.
and the mercury.
That is correct. And mathematically, that's exactly what will happen between these two terms.
So like your first term with water, that's just finding the pressure like at the bottom?
Right here. This plus this is the pressure. Well, see, an H2 really doesn't come all the way to here. It's really the pressure here
Okay.
is what it amounts to. Does that make sense?
Mhm.
All right.
So we don't really care how deep that tank is, do
Right, as long as we care how far it comes back up again. Yeah.
Just hold water off to the side.
That's right, because what it goes down and what it goes up will exactly subtract off of each other, and everywhere that you're at the same level, as long as the fluid is continuous, the pressures will be the same level. Yep, very good point. Yes?
So if atmospheric pressure isn't given in a problem, is it just zero?
No, it's because it says gauge pressure. So gauge pressure does not include atmospheric pressure. If it didn't give it, you would have to, if it said I want atmospheric pressure of, or absolute pressure of that, you would have to add in a standard measurement for atmospheric pressure. You would have to say, like, I assume that atmospheric pressure is 14.7 psi, or I assume that atmospheric pressure is 101 kPa. Exactly.
Why is the oil added and the mercury subtracted?
Okay, so if we start here, in the oil, we end up going down, which is positive. In the mercury, we end up going up, which is subtracted.
Oh, because we have less pressure.
That's right.
Okay, that makes sense.
Yes, exactly. Because the pressure at the bottom of a column is higher than the pressure at the top.
Okay, that makes sense.
Perfect. Good question. What other questions do you have?
When we're solving for P1, it's not just the air pressure thing.
They're the same. If you look at the picture, what would happen if this air were more pressurized? What would happen to the water? Right. So the fact that this is in equilibrium means that the pressure on this side of the interface and the pressure on this side of the interface have to be exactly the same. Otherwise, the picture would look different. I mean, that's a little hard to see in the picture. I mean, it's hard to see if you just see a picture drawn and you're like, well, but if you think about the mechanics of it, if this system is in equilibrium, in other words, if it's not fluctuating, the pressure in the air and the pressure at the interface of the water have to be the same.
So I'm still confused about what you did with H2 with respect to water.
Okay, well, okay, how about if we just do this? How about if we just say, the water here is H1 below the interface. Let's just do that. So then it's just P1 to get to here plus rho GH1. So what I did was I said you could, really the column is this, right? So I added both of these together, which I said were H2 and H1. It's really not because there's also this elbow. But then when you come back up, you would have to subtract off H2. So you add in H2 going down, you subtract off H2. Rho GH1, rho GH2, you subtract, you add going up, add going down. So they go away. And you can see that in this equation. We have rho of the water times G times H1 plus H2. And then we subtract off rho GH2. So mathematically those go away. And it's just rho GH1. Got it?
So, and then I think he asked the same question.
Yeah.
P2 is just zero because we assume.
It's gauge. We're not really assuming. We're just saying it's gauge pressure. So if you hold a pressure gauge in the atmosphere, I just take a tire gauge and I hold it right here. What does it read? Right. That's exactly right. It reads zero. So that's what they're getting at. They're just saying the pressure, the increased or decreased pressure of the air-water interface in the tank compared to the atmosphere.
And then also our P1 absolute minus atmospheric, that will be gauge 2 as well.
P1 minus P1 plus atmospheric would be P absolute at 0.1. So like if you got a value of 13 psi right here, and if you said that the atmospheric pressure was 14, you could add those two together, and that would be the absolute pressure of the tank.
Okay.
Yeah, good question. What other questions? Yes.
What's the Thursday looking like? Are we going to be doing answering questions?
We are going to continue in chapter 2. Yes. So we'll be in chapter 2 today, Thursday, probably Tuesday of next week. And then we'll have our test over chapter 1 either Thursday of next week or the following Tuesday. I'm not sure yet, but as we get closer, I'll let you know. Till the, right. Although, really, like I said, I wanted to make sure to go over the homework today because this is quite complicated, and if you're trying to learn it the night before the test, you will not be doing yourself any favors, so. But yeah, I don't collect till the test.
Fluids the same
No, fluids, we're collecting chapter 1 tomorrow.
Okay.
That is correct. We won't have a test. Well, same thing. Chapter 1, chapter 2 will be an exam. But in fluids, I'm collecting in between. And really, the reason for that is I have 5 people in Laramie. I only know one of them, so I don't really know them. So I just want to make sure everybody stays on task. Yep.
But I have a question on
Yes.
61.
On 61?
Yeah, I just had a hard time visualizing it by the
Let's-
reservoir.
Okay.
'Cause I saw it as like, I don't know, septic.
A hydraulic lift in a car repair shop has an output diameter of 30 centimeters. Diameter. Okay. And is to lift a car of 2,000 kilograms. Determine the fluid gauge pressure that must be maintained in the reservoir.
So I just meant inside the hydraulic, right?
Yep.
Okay.
That's all they're getting at.
That's all.
Yep.
The question was
Yep. So you just convert 2,000 kilograms into a weight, and then divide that weight by the area of that hydraulic cylinder. It's kind of neat the way hydraulics work, because if you think about, like, you take a big reservoir, if you have a fluid column, I mean, this is how they really work, right? And you have a big one, and you push on the little bit, you end up pushing a lot on the little one. So that's kind of neat. Because the pressure is continuous, except for the difference in elevation. Well, the pressure is continuous, but it's the same plus or minus the height difference, which you reach. Now, there's some other things about this too, is like certain fluids are chosen for certain behaviors. And one of the things, like when we look at that problem that we just talked about right here, water and air are immiscible, meaning they form an interface that's pretty clear, until you get to a really, really high pressure. So that's another thing. Like when you choose a hydraulic fluid, one of the things that you're choosing is something that's not overly compressible. Because if it's overly compressible, you have some different effects going on. Same thing here. If this interface were not clear, in other words, if the air and the water were not clearly separate, if it were a miscible interface, you'd have another set of problems. It's not that you can't always use it, but in mechanical systems, those are generally unnecessary complications. So you choose fluids from an engineering point of view that behave the way that you want them to behave. Okay. Other questions? All righty. So we'll start with chapter 2 today, and then we'll have homework assigned, of course, and then, like I said, we'll spend 3 lecture days on chapter 2, and then we'll either have our exam next Thursday or the following Tuesday. So either a week and a half from now or 2 weeks from now. I'm thinking a week and a half, really, to tell you the truth, but we'll see how it goes. So, chapter 2 talks about the idea of energy. And one nice thing about energy that we will use, and that is actually a statement of the first law of thermodynamics, is that energy is conserved. So, all it does, it changes form. Now, the only time that this is not true is in the event of a nuclear reaction. And you may have seen Einstein's formula, E is equal to mc squared, which literally is an equation, meaning this is equal. And it means 2 different things. It means a lot of different things. But basically, mass multiplied by the speed of light squared is equal to energy. So two things that this equation means. One is that if you blow up in a nuclear reaction a tiny little amount of mass, because the speed of light is very, very large, and when you square it, it's very, 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 very large. When you multiply a tiny amount of mass by the speed of light, or you accelerate a little tiny bit of mass at the speed of light, you get incredible amounts of energy. The other thing it means is that to accelerate a tiny amount of mass to the speed of light requires incredible amounts of energy, which is why, one of the reasons why there's sort of a wall at the speed of light in terms of anything that has mass does not seem to be able to travel beyond the speed of light, or at the speed of light even. Massless particles, which kind of sounds like a contradiction in terms, but in quantum physics it's not, but massless particles are exempt from this because that equation doesn't apply. If mass is zero, they can travel faster than the speed of light all they want. So, but in our case, we're not going to be talking about nuclear reactions. We are instead going to be talking about mechanical systems. And mechanical systems is a very broad term. For mechanical systems, energy is conserved but takes different forms. And from your work in vector mechanics, in physics and statics and dynamics, you probably remember that there is one form of energy is called kinetic energy. Another form of energy is called potential energy. And there's an example, there's many, many examples of one form changing into another. For example, if you have an object that drops over a cliff, up here it's all potential energy, which is mgh energy. And if it falls down the cliff in a frictionless pattern, just before it hits the ground, it turns into kinetic energy, or 1/2 mv squared. So without friction, you can say that mgh is equal to 1/2 mv squared right before it hits the ground. When it hits the ground, the energy goes into changing the form of the object, into breaking it or splintering it or mashing it up or whatever. But 1 second before it hits the ground, this can be said to be true. Now, if you look at the units on this, or let's look at units. Look at the SI system. We could say kilogram meter per second squared times meter, kilogram meter squared per second squared. What does that equal? Well, if you think about force equals mass times acceleration, you know that a kilogram meter per second squared is a Newton, and so this is equal to a Newton meter. And the unit for a Newton meter is a joule. Now if you look at the other side of the equation, once again you can see mass, kilogram. V is meter per second squared and squared. That is also a kilogram meter per second squared times meter, which is a Newton meter, which is a joule. Okay, so these are the units of energy. Energy can be transformed into heat and work. And if you remember, work is equal to a differential equation or an integral of force times acting through distance, a dot product. So there's a couple of consequences of this. One is you can see it's a force times a distance, for example, Newton times meter, so we're still back at the same units. The other thing is because it's a dot product or a scalar product, work is a scalar. So one of the nice things about energy, including heat and work, is that energy, work, heat are all scalars, not vector. So what that means is they're all amounts. That's why conservation works. We don't have to talk about energy in a particular direction. Energy is just energy. So there's an amount, and if you change it into forms, you use a certain amount, you convert a certain amount of potential energy to kinetic energy and so forth. But it's after coming out of statics and dynamics and physics 1, it's kind of nice that we're back in the realm of algebraic quantities rather than doing vector math at this point. So in general, and this is quite a common symbolism, energy, work, heat, and let's include some forms such as kinetic energy, potential energy, and one that we're going to learn about a little bit in just a few minutes here, internal energy, are all designated with capital symbols. If you take that extensive energy and divide it by mass, you designate the same quantity with a little letter. This should just be an E. It's just my handwriting that looks weird. So in other words, capital E divided by M is designated by little e. Capital kinetic energy divided by mass is designated by little ke. And similarly, capital PE over M is designated by, they call it minuscule or small PE, and little u divided by mass is, capital U divided by mass is little u. We can do similar things for work and heat. Work over mass is equal to little w, and heat over m is equal to little h. Although heat is generally designated by the letter capital Q. So therefore, I would say Q over M is equal to little q. Now I bring this up. The letter Q, when we start talking about heat, or we start talking about thermodynamics in general and fluid dynamics, Q is a very, very overused letter of the alphabet. There are a lot of things that are designated by Q. And just like reading, you have to sort of pick it out by context. So I make that distinction. H is actually reserved for another type of energy, which is called enthalpy, or pronounced enthalpy, or some of the, I try to pronounce it enthalpy in order to distinguish it from something else called entropy later on. But H is sort of, like I said, it's more reserved for this particular kind of energy called enthalpy rather than heat. But since we start our conversation here, it's important to note. It's also important to note that Q is just used everywhere. And the two biggest abuses of the letter Q, in my opinion, are heat and volumetric flow rate. In this textbook, we use a different symbol for volumetric flow rate, but it is common in the industry, and in your fluids book, to designate volumetric flow rate by Q. The two are very easy to get confused. So that's kind of why I wanted to bring that up at this point. All right, so let's go back to energy. If energy is measured in joules, little energy is just measured in joules per meter. And we can also talk about flow rate, or E dot. Dot is that notation that just refers to the first derivative with respect to time. So E dot is energy per time. Little e dot would be little e per time. And the units on E per time would be like joules per second, which of course is a watt. Okay, Little e per time could also be capital E over mass times time. Right? And so that pattern of symbols carries through. So in other words, W dot is work per time, which is power. Has the same units. It's still in watts. I don't know why that was up there. All right. So, in general, there are a lot of different kinds of energy that we can talk about. For example, U, internal energy, PE, potential energy, KE, are the main forms of mechanical energy. However, in some instances, we may be concerned with electrical energy. We may also be concerned with, there's one called the energy of surface tension, which is interesting. It's an interesting fluid property, which I'll describe in just a minute. I'll just put in a lot of other ones. Okay, these are the three that we're going to be talking about, along with heat and work, for the most part. Electrical energy, obviously, is just the flow of, or the ability to do work by an electrical circuit. If you have a fluid, like if you have a container, think about when you were a kid maybe and you dyed Easter eggs. Okay, if you had a container full of dye, and you have that little bent wire, I'm going to draw it in top view, that you would sit an egg on. Okay? And as you dip, if you don't have an egg, let's leave the egg off just for the sake of simplicity. If you dip this inside of the fluid and pull it up evenly and slowly, what do you think happens to the surface of the fluid as you pull that through? Was anybody a weird enough kid like I was to watch what happens? Yeah, it comes up with it, doesn't it? That's exactly right. It clings to that wire as you pull it up. This is the same kind of energy as when you blow bubbles. Like if you have soap bubbles, that's the same kind of energy that keeps, that allows you to do that. You can take a film that will stretch over a bubble wand that you can blow a bubble onto. And that is just called the energy of surface tension. What actually happens is the surface tension of different fluids is different. I mean, it's a physical property of a particular kind of a fluid. But what happens is, in the simplest sense, in the physical or the mechanical sense, the fluid prefers to adhere to itself, or the molecules of the fluid are denser than the molecules of the vapor above it, and so there's more attraction between the molecules of the fluid than there is between the molecules of the fluid and the molecules of the vapor or the air above it. And so when you come out through that fluid, there's a desire for the fluid to stay together rather than to disperse. And that's just referred to as surface tension. Yeah?
Isn't it also called cohesion?
Well, it can be called, there's cohesion and adhesion, which are really closely related to each other. What has to do with cohesion and adhesion, talk about the preferential behavior of different fluids to either adhere to themselves or adhere to other things. So, like, that's the effect that you see in a meniscus in an evacuated cylinder of any sort. Like if you have an evacuated tube and you put a fluid in it, some fluids will have a meniscus that goes up, some fluids will have a meniscus that goes down, some will be rather flat. None of them really are 100% flat, but that angle that it attaches to the sides of the column or that it adheses to itself is actually closely related to this idea. So yeah, very good. See, you guys are smart. You know all kinds of stuff. So anyway, fluid behavior is pretty interesting. But there are other types of energy that are generally not going to be our consideration at this point. In most cases, in most mechanical systems, we can say that E total is equal to U plus PE plus KE. Or similarly, that little e total is equal to U plus PE plus KE. And since energy is conserved, E total at time 1 is equal to E total at time 2 if no energy leaves the system. Leaves or enters, I should say. Okay, so you can still have these changes of forms within the system. At time 1 equals U plus PE plus KE at time 2. So this asks a lot of questions that we're going to address today and in the immediate future. But for now, let's talk a little bit about internal energy. U, because I think we already are fairly familiar with potential energy and kinetic energy. So let's talk a little bit about internal energy. Okay, so internal energy is an expression, is a macroscopic or measurable in the physical world, or a gross property of the molecular energy of a system. And that can be, the system can be a fluid, meaning either gas or liquid, or solid, or combination. Okay? And so basically, if you have, let's say you have a glass of lukewarm water, and next to it you have a glass of very hot water. This is TH, high temperature, low temperature. If these are the same fluid, which of these do you think is going to exist at a higher energy state? Absolutely. This has more energy associated with it. So UH, in this case, is going to be greater than U sub L. Right? So how did we get, if we start out with cold water, how do we get more energy into it to make it hot water? We obviously have to put some energy into it, right? And in this case, it's probably going to be in the form of heat. But you could do it a lot of different ways. I mean, you could stick an electrode into it. You could shake it up really hard. You know, you can do all kinds of things. But there's a lot of different ways to put energy into a system. But there's a bunch of different things that figure into this. One of them is that the molecules of hot water are just moving more quickly. They're vibrating more quickly and they're rotating more quickly. They just have more energy associated with them. And the internal energy of that system is just a measure of sort of all of those things put together. So in general, internal energy can be tabulated. In other words, we can assign values to it for a particular substance at a particular state. And if you remember, we talked about a state as being two independent physical properties. So if you have a liquid, if you have water at 70 degrees centigrade and 1 atmosphere of pressure, you can say conclusively what the internal energy of that water is. If you raise the temperature, the internal energy is going to go up. If you change it, if you decrease the pressure, the internal energy is going to change in one way or the other. But you can always account for it. So in other words, if you have water at 70 degrees and 1 atmosphere, it doesn't matter, don't mean to dissuade any people that buy their water from Fiji or anything like this, but water is water. I mean, that's the truth right there. And it's the ultimate recyclable product, absolutely. So if you have water at 1 atmosphere pressure at 80 degrees and there's no impurities in it, its behavior, its physical characteristics are exactly the same as any other pure water at 80 degrees and 1 atmosphere pressure, regardless of whether one bottle of water came from Fiji and the other one came out of a ditch. As long as you clean out the stuff that was in it, as long as you filter it, or do whatever you need to do. Now, saline is a different issue. I mean, saline is the same idea, but water that is salty, it's very hard to separate salt out of water because it's an ionic compound, and so the Israelis are working on it, but because they have a lot of salt water and they don't have any other water, so they'd really like to be able to desalinate water. So it's very difficult. It's actually easier, not meaning to be gross, but it's way easier to clean up sewage than it is to clean up salt water for human consumption. So there you go. And we'll just leave it at that. We won't talk about that anymore. But the internal energy is a state function. So it can be tabulated because it is a state function. Now, the last thing that we're going to talk about, right now it's 11:36. I'm going to talk for no more than 9 more minutes. We're going to get out by 45 because I have a meeting at noon. But if you have, tell me about water. Tell me, what do you know about water? Water is great. It's called the universal solvent because it has that slightly polarized electrical charge because it's H2O. And so you have an oxygen and 2 hydrogens. These are both positives, so they sort of push each other apart. And there's a slight electrical charge associated with it. So it dissolves a lot of stuff. One of the other things that's really interesting about water is on planet Earth, it is ubiquitous. Anybody know what ubiquitous means? Kind of a $5 word. It means it's everywhere, you know. And this is sort of an engineering thing. Why do we study water so much? Why does water have its own name, hydraulics? Why? Well, it's just because it's everywhere, you know. So water is ubiquitous, water is a universal solvent, and water is really cool because it maintains a state very, very well. It also has an extremely high specific heat, which is a really interesting feature of water. So for example, if you put it in your radiator of your car, as long as it doesn't freeze, it's going to pull heat away from the engine very, very efficiently. Okay, so those are just some other ideas. But water exists in several states. And state really refers to any 2 independent variables. And so when we think about water changing from what we might call one state to the other, what we're really talking about are phases. And there are several phases of water, but there are 3 predominant phases. Does anyone know what those are? I bet you do. Solid, which we call ice.
Liquid and gas.
That's right, liquid, which we just call water, and gas, which we call steam. There are other phases as well. But one of the interesting things about water is all 3 of these phases are really well defined, and the changes between those phases are really well defined as well. So we'll talk about that in great detail as we continue on in this chapter. Now, let me see where I want to go with this. I think the last thing I want to do is to introduce you to this idea, although it's not really in chapter 2. We're going to study this pretty extensively. But in general, let's go back, I guess, to this one. Solid ice exists at low temp and, generally speaking, higher pressures. So any set of conditions that fall into a range that will put the ice in an organized enough fashion or at a low enough energy state will cause the water to exist as ice. liquid water tends to exist at intermediate temperatures and intermediate pressures, and gas at high temp and low pressure. Okay. And we also have clearly defined interfaces between each of these. So, for example, if we go from a solid to a liquid, if we're going from solid to liquid, we call that melting. If we go the opposite way, liquid to solid, what do we call that? Freezing, right? If we go from a liquid to a gas, what is that called? Yep, evaporation or vaporization. And the other way? Called condensing. Right. And of course, there's also an interface that we don't see because it occurs at relatively low pressures, not pressures that we typically see in everyday life. But there is an interface between a solid and a gas, which has the same name going back and forth. Does anyone know what that is? Yeah, sublimation. Very good. Okay, and we don't see water do that because sublimation for water tends to occur at low pressures. Now, the one thing I would say also is each of these occurs at a set of conditions. So, for example, if we think about, let's think about liquid to gas. That's kind of this is the one that's really interesting for water. But when we take liquid and we boil it, you can do it at like an atmospheric pressure and 100 degrees centigrade. What happens if you have a lower pressure, like here, where we're about, instead of being in an atmosphere, we're maybe 7/10 of an atmosphere, about 7/8 of an atmosphere. Well, where does it boil? What's that? Yeah, the temperature's lower, isn't it? So in other words, you really don't get up to 100 degrees centigrade. It boils at about 94, 95 degrees at our altitude. There are actually places in the Andes Mountains where, like, if you take a pot of water and you boil it with potatoes in it, the potatoes will never cook. They will never cook because you never get enough heat into that. So how do we remedy that? Like, if any of you ever have, anybody in your house ever canned food? Yeah, that's kind of lost art, but it's really cool. So when you can food, a lot of times you'll use a pressure cooker. The reason that you use a pressure cooker is to kill more bacteria by getting a higher temperature. But the way you get a higher temperature is to increase the pressure. So you take the same substance, whatever it is, if you're making, I don't know, choke cherry jelly, and you want to boil it and you want to make sure all the bacteria are dead, you would prefer to get the temperature up higher. Without increasing the pressure, you can't do that. And the temperature increase is really what kills the bacteria. So anyway, there is one substance that sublimates in the atmosphere. Does anyone know what that is? There's several, but I mean, there's one that is pretty common. Yeah, it's dry ice. And does anyone know what dry ice is chemically? It's just carbon dioxide. So solid carbon dioxide is called dry ice. And the reason, like, if you're going to send, I don't know, something to somebody, you want to send a package of T-bone steaks that are frozen. You'll freeze them, but then you don't want to pack it with regular ice, with water ice, because when the outer ice melts, it gets all soggy, and then your T-bones are going to be all soggy, and everything will be a mess. So what you can do is you can pack it with dry ice, because at atmospheric conditions, dry ice will just evaporate. And so it will stay cold. It's also a little colder than regular ice, but the big thing is it doesn't make a mess because it just vaporizes. So you can pack, like if you get steaks from Omaha Steaks or something like that, you can pack it in a special cardboard container, or styrofoam will actually absorb it, which is kind of weird. I mean, it just kind of goes out through the styrofoam. You pack it in a cardboard container with holes inside, or you can put it in styrofoam, and it'll just melt. It'll just go away. It'll just sublimate. So, very cool. So these ideas of interfaces between states, or between phases, to be more accurate, is a big subject of thermodynamics, which we'll talk about a lot more. But that's it for today. There's no homework today, but I will trust that you'll be 100% finished with your Chapter 1 homework, and you'll understand how to run a manometer, and we'll be good to go. Then on Thursday we'll come back. We'll talk more about energy transfer. We'll talk specifically about heat and work. and we'll start to develop some equations. So that's it for today, ladies and gentlemen. Have a wonderful day, and we'll see you Thursday.